Hello, math students. This lesson is going to be on building quadratic functions to describe revenue. The warm-up question is a review question from yesterday's lesson where we talked about building quadratic functions to describe objects that are launched into the air or falling through the air. And so go ahead and try pausing this video now to try those warm-up questions and then come back to get the answers. So to be able to answer this question, it has to do with the three terms that show up in a quadratic equation and what each of those terms tell us. In yesterday's lesson, we learned that if you want to know the speed, it's always going to be that linear term there, which is going to be the term that has the variable, and here 20t, not the variable squared. And then in our second equation, we've got that linear term is the 45t. So for which football is traveling at a faster speed? This first one is traveling at 20 feet per second, and then the second one is traveling at 45 feet per second. And so that second one is going to be at the faster speed. I'm going to say the second football. Number 2 asks about the term negative 16t squared and why it's in both equations. Yesterday we learned that that quadratic term, so here the negative 16t squared that shows up for both of them, is describing the effect of gravity. It's negative because gravity pulls objects down, and so it's decreasing the height as time goes by. And so both of those equations have negative 16t squared because the first football and the second football have gravity impacting them, right? Gravity's pulling both of those footballs down to the ground. And so why is the term in both equations? We can say it's because the effect of gravity, and gravity affects both footballs. And then for that final question, number 3, it says Joseph and Derby threw the 2 footballs. If Derby is taller, which equation most likely represents the football he threw? This has to do with that final term we haven't talked about yet. It's that constant number. And so that number that's all by itself without a variable. We said that constant in each equation tells you about the starting point. It tells you the height when time is 0. And so here we're told that Derby is the one who's taller. And so if he's taller, it means his football is probably starting at a taller height. This first football is starting at a height of 6 feet. The second football is starting at a height of 5 feet. And so Derby's football is most likely the one in that first equation, the f of t equation, or our first equation. We know that because it is starting at a height of 6 feet. And so this is one of the big things we had talked about in yesterday's lesson, where we were looking at equations like these that represent objects that are falling through the sky or getting launched into the air and then coming down like those footballs are. We're going to go ahead and jump into today's lesson. And in this lesson, there are 2 objectives. The first is that we can model revenue with quadratic equations and graphs. I want to pull out a couple words here. The first one, revenue. When you talk about revenue, hopefully money is coming to mind. When you talk about revenue, that's the money that businesses or individuals are bringing in to their business. It's the money you make. The second word I want to point out is quadratic. This whole unit is about quadratics, so of course we're talking about quadratics in this lesson. One of the things I've been emphasizing is if you're looking at a quadratic equation, in order to be a quadratic equation, it has to have what in it? And I can come up to these equations to point it out. It's that term that I underlined in green, that quadratic term. And I know it's quadratic because it's got a variable squared. Here it's t squared. In some other equations, it might be n squared or x squared, but it's going to have that squared term somewhere in the equation. If it didn't have that, then it wouldn't be quadratic. So we're going to be looking at quadratic equations and then also their graphs. The other thing we did in yesterday's lesson, besides talking about those 3 terms in quadratic equations, is we introduced for the first time what a quadratic graph looks like. And we said quadratic graphs are those U-shaped curves. We said yesterday sometimes the U's face up, sometimes they face downwards, and we called those graphs parabolas. Anytime you graph a quadratic equation, it gives you the graph of a parabola. And so we're going to be looking at talking about revenue and representing those stories about revenue with quadratic equations and quadratic graphs. The other thing we're doing in this lesson is identifying domain. Domain goes all the way back to Unit 4 that we had talked about on functions at the beginning of this class. Do you remember what domain is? Domain, we said, are all possible inputs. When you're talking about a function, you're thinking about all the different possible inputs for that situation. And so we are also going to be looking at the domain of the different quadratic situations in this lesson. We're going to start off with this story here. In this story, we've got a company that sells movies online is deciding how much to charge customers to download a new movie. Based on data from previous scales, they predict if they charge X dollars for each download, then the number of downloads in thousands is 18 minus X. As we consider the story, there's a couple things I want to have you think about. First, we've got this company. What is the company doing? Well, they're selling movies online. And what is our story going to be all about? We're talking about how much they should charge, what the cost should be to download a new movie. So they're trying to figure out what the price should be for these movies they sell online. And then they give us some stuff in algebra, right? They give us these variables here. And so we've got, based on data from previous sales, looking at in the past when they've sold other movies, they're predicting this relationship that if they charge X dollars for each download, the number of downloads in thousands is 18 minus X. So X is going to be, I'm going to say the price for a download. And they have figured out, based on their personal data, this isn't always true, but for their personal experience, that 18 minus X, what's that represent? The number of downloads. We've got the number of downloads, and not just the number of downloads, but the number of downloads in thousands. That's important. So number of downloads in thousands. Just pause here for a moment and think about, if you were this company, what would you do? Would you want to set a really low price to make the most money? Would you set a really high price to make the most money? What would your strategy be? Well, that's what we're going to be exploring below. And just like a lot of our situations, we're going to start with a table to help us understand the situation a little more. So using the information they've given, this first row here has already been figured out for us. We've got, if the price is 3, so if it costs $3 for each download, the number of downloads in thousands is 15. I want to pause there because we're going to have to do the rest of this table. Where do you think they got 15 from? Well, we were told the number of downloads in thousands is 18 minus X, and we were told that X is the price for each download. And so here, if the price is 3, we're doing 18 minus 3 to get that 15. You're just putting 3 in for X. So that's the first thing we need to do, is figure out how we calculate the number of downloads. The last column here is about revenue, and we said revenue is the money you make. And so they have figured out if they price each movie at $3, they're going to make not $15, but $15,000. Oh, I'm sorry, I said make. They're not making $15,000. They're going to sell 15,000 downloads. The question we need to figure out then is, how much money do they make? They got 45 here. Can you see what math they did to get to the 45? Well, it's multiplication. We're taking the $3 for each download multiplied by the number of downloads. So 3 times 15, that gives us the 45. And so they're not making $15,000, they're making $45,000. Even better. We're going to fill this out for a couple different prices. Notice these aren't all the possible prices. You could also sell a movie for $1. You could sell a movie for $10.50. But we've just got a couple random numbers here to help us notice what's happening as you change the price. So think for a moment, what do you predict we're going to see happen as we increase the price more and more and more? Do you have any predictions? Well, that's what we're going to see as we finish filling out this table. I'm going to do one more and then encourage you to pause and try to figure out the rest. If we change the price to $5, how would I find the number of downloads? Well, it goes back to that 18 minus x, except here I would be doing 18 minus 5, and that would tell me 13. They are going to have 13,000 downloads. And so then to find the revenue, how much money they're making, well, they're selling 13,000 movies, but this time they're $5 each. So we're taking that price, $5, times how many movies they're selling, and figuring out that would be $65,000 in revenue. So right away, I'm noticing if the price goes up, they are making more money. That's interesting. Go ahead, use these first two as examples and pause the video to fill in the table for the remaining prices. Don't worry about X yet. Just focus on $10, $12, $15, and $18. Okay. I went ahead and I filled in the next couple. So we've got if they sell each movie for $10, 18 minus 10 means they would be selling 8,000 downloads. And then $10 times the 8,000 means they would be making $80,000. And so just like we saw above, we upped the price and we're making even more money. But notice for the next two, the $12 for each movie and the $15 for each movie, I ended up getting that the revenue is going back down here. It's decreasing. For each movie costing $12, they would predict to make $72,000. And if they make each movie $15, they're predicting to make $45,000. Think about why that is. In the past, I've had some students say, well, yeah, if the movies are really cheap, you're going to have a lot of people buy them. And that's what we're seeing here in the middle column. But if the movies are too cheap, it's not a great way to make a lot of money. And then the opposite, right? If the movie price is really high, you can make a lot of money from selling one. But if the price is really high, you're not going to have a lot of people be willing to pay that much money. And so we see here the best strategy is not going to be to make them as cheap as possible. It's not going to be to make them as expensive as possible. We're seeing it kind of increases in revenue and then decreases. I did save the last one, the $18 to do on camera. If each movie cost $18, their prediction of how many they would sell is 18 minus 18 is 0. So if the price for a single movie online is $18 each, they're predicting based on their 18 minus X that they would end up selling 0 of them. And if you sell 0 of them, what's your revenue? How much money are you making? Well, $18 each times 0 just means you would be making $0. You don't make any money there. And so we're seeing if you make the price way too high, you don't end up making any money because no one's interested in buying them. This final row here with X is going to be describing what we've been doing above. This first one has already kind of been done for us because they gave us that expression. We've been using for this middle column 18 minus X each time to find the number of downloads. If you look at what we've got here, every single time we were taking 18 and subtracting a number, and that number every single time was this first number, our X. To get this final row here, what did we have to do every single time? Well, notice I was doing, for the first one, 3 times 15 to get 45. I was doing 10 times 8 to get 80. I was doing 15 times 3 to get 45. So for this final one, I'm going to be doing X times 18 minus X. And I can write that out by saying X times 18 minus X. This expression right here represents the revenue. And I could always check it against these ones I have above. For example, if the price was 10, if X is 10, this is saying 10 times 18 minus 10 would give me the revenue. And 10 times 18 minus 10 is 8. That does, in fact, give us the revenue. So don't forget, if you don't feel confident about writing these out, you can always use one of these previous rows to check your answer. So this right here this final expression represents the revenue, which we know by the name of this lesson, that's what we're focused in on. And so below, I've got, this is the same table we just made. That final column, that final row in our table is what we had just talked through about that revenue being x times 18 minus x. And the question I want us to think about is up here on the left. Is the relationship between the price of the movie and the revenue in thousands of dollars quadratic? Explain how you know it is or is not. You need to take a moment to pause the video here and think through that question. Go for it, and then come back when you're ready to hear the answer. Well, in the past, I've had students say, well, we keep talking about how quadratic means x squared. And I'm looking at this final one, and I don't see an x squared, so I don't think it is. And if you were thinking that, I understand where you're coming from. I think at the very beginning of this lesson, right, we were quadratic means it's got an x squared term. If you think back to those lessons we had done on those quadratic patterns, sometimes that x squared can be hiding. And sometimes you're not going to see an x squared because think about what x squared means. X squared means you are doing x times x. And so if the only thing you look for is x squared, it's not written as x squared, you might not see it. But if you think about x squared means x times x, we do have that here in this expression. I need to move it down a little bit so we can see. I know this final expression here is a quadratic expression because notice if we multiply it out, if we distribute, x times 18 is 18x. And here it is, x times x is that x squared. This is a quadratic. Oh, do I have enough room? Yes. It is a quadratic because it's got that x times x in it, which is the same thing as x squared. And also, this lesson is on representing revenue with quadratic functions. And so we did have a little hint by the title. So thinking about revenue, it's represented with a quadratic. I do want to answer real quick. In class, sometimes people ask, so does this expression always represent revenue? Not always. Remember that company said 18 minus X modeled for them based on past sales, what they would predict the number of downloads to be. Different companies are going to have different expressions for that. But there is this idea of, in order to find the revenue, you would be multiplying the price, this variable, times the number of downloads, which is another variable. And so you get that X times X there. Also, when you think about revenue, even if the numbers are a little different, when we go to graph it, it's going to look the same for a lot of different situations, not just this one. In order to graph this, I'm going to need to move my face. And in order to graph this, we are going to be using some of these numbers from that table we made. It says plot the points that represent the revenue as a function of the download in dollars. So I'm really focused on the price and the revenue, not so much that middle row. When we go to graph it then, the first one we've got is if the price is $3, the revenue is $45,000. So on my graph, I would go to 3. That's going to be around the middle here of this box, and then up to 45,000. That line there is 50, so I know 45,000 would be just a little less than it. The next point, if the price is $5, the revenue is 65. So I'm going to go over to $5, and 65 would be somewhere here. And $10, the revenue is 80. I'm guessing that is around here. $12, the revenue is 72,000. So that's going to be a little lower, maybe like right here. $15, we're back at 45. So I'm going to make sure that point there is equal height to that first one I did at 45,000. And then that final point, we have $18. We've said they're not going to be getting any money. That revenue is 0. So we are down here. Now, looking at this graph, right, remember we had said these aren't all the possible prices. You could be selling a movie for $1, $2, $3, $4. It could also be decimals. It could be $15.30. And so we had only calculated a few of these. But if you were to graph all of those possible points, if you were to turn this into a graph of a line, that graph, when you connect all those points, is going to look something like this. Theirs is zoomed in a little more. Notice their scale's got 10, 20. They've got they're counting up by 10 for every line on their y-axis. And so we get a real good look at what that graph would look like. And hopefully this graph does look familiar because it goes back to what we had said yesterday. It's a quadratic expression, and we are getting a quadratic graph. We are looking right now at a parabola, that U-shaped curve graph. Looking at this graph, it tells us a lot more information than this table does. I can see the predicted revenue for any price. So for example, the first price I had in our table is $3, but I can see stuff before 3. I could see what they would predict to make around $1 per movie, $2 per movie. I can see $6, $9, $12, $15, $18. I can see all of those different points. And so looking at this entire graph, the question is, when my face moves, what price would you recommend the company charge for a new movie? Using this graph now, and not just the table, what would you recommend they sell the movie for? When I do this in class, lots of times students focus in on the table and they say, well, that $10 looks pretty good. It looks like the highest possible revenue. But now that we've got the full graph, I do see there's points where it gets a little above $80,000. I'm looking right here. You see how it goes just a little bit above that $80,000 line? There's a point right here that would make them the most money. And if they were asking me, I would recommend they set the price where they predict they're going to make the most money. And so if I'm trying to describe that point there, it's right there in the middle of our graph, and it is at the price $9. It's not in here in the question, but I do also like to ask the question of, what would you not recommend they sell that movie for? And I've had students say, well, anything that's not $9, right? Because anything not $9, they're predicting to be less. And that is a very fair answer. I've also had students say, well, you really shouldn't sell it for $18 because $18 you predict to make no money. We had that point, $18 at a revenue of $0. And I agree. If you set it for $18 or notice anything more than $18, you're not predicting that you're going to make money. Is there any other point where you would say, nope, don't do that? There's one other place on this graph that shows that they wouldn't make money, and it's right here. And that hopefully makes sense as well. If they set the price of their movie at $0, they're definitely not going to make movie. If you're selling free movies, how are you going to make money? And so we see those 2 points there that I marked in green are those points where they wouldn't make any money. I would recommend, of course, that you're setting it for the point or the price where you make the most revenue. But any of these other prices would make them some money. But $0 or $18, this graph is showing that they wouldn't make anything. These 3 points that we have marked on the graph are really important when you're trying to understand graphs of quadratic situations. And those 3 points have names, which one of them is peeking up there at the bottom. But the first point is the vertex. Up here on this graph, the vertex was that point I marked in blue. The vertex of a quadratic graph is going to be the point where the graph changes from increasing to decreasing. And when you look at these graphs of parabolas, it is the highest or lowest point on a graph. This vertex here, this is not a parabola because it's not a curve, but we're seeing it's that point where it changes from decreasing to increasing, and it's also the lowest point on the graph. Here we've got, this is a parabola, and it's that point where it changes from increasing to decreasing, and it's the highest point on the graph. With parabolas, it just depends on which way that parabola is going. The vertex might be the lowest point, or it might be the highest point, but you're going to find it in the middle of the graph where it changes direction. The other point that's really important for us to understand as we're looking at quadratic graphs are called the zeros of a function. And it's not very cleverly named. It's very easily named. The zero of a function is just where the output is 0. And so up here, our zeros were these 2 points. These are called the zeros because it's the 2 prices where the revenue would be 0. If they sell a movie for $18, we predicted that they would make $0 in revenue. So we say that 18 is a 0. Same thing for 0. If you set a movie price at $0 and it's a free movie, the revenue would be 0. So 0 is also a 0 of the function. And so these are our 2 new vocabulary words for this lesson here, the zeros of a function and vertex. Just to give you more examples of zeros, for this graph here, the zeros would be these 2 points here. I know those are the zeros because it's where the y-coordinate or the output is 0. And similarly, for this parabola here, these 2 points would be your zeros. I know that because it's where it's points on our x-axis where you don't have to go up or down, right? The output or that y-coordinate would be 0. And so for the rest of this lesson, we are going to be focusing on these points and also bringing in domain. Remember, we said the other objective of this lesson is to talk about domain of quadratic functions. We're going to look at a couple different situations. Some of them are going to be hopefully familiar because they're situations we've covered in previous lessons, and talk about the vertex, the zero, and the domain, and what all 3 of those things tell us about a situation. To help give you an idea of what we're going to do, these would be the 3 questions I'm asking. We've already talked for this one about revenue, what the zeros and the vertex are. So if I asked you what are the zeros and what do they represent? The zeros, we said you can find right here on your x-axis. The zeros are 0 and 18. You could even write them if you wanted as a coordinate. So let me show you what that would look like. One of them is the coordinate 0, 0. And the other one is the coordinate 18, 0. And what do they represent? They represent the movie prices that result in $0 of revenue. So that's going to be one question we practice, is identifying the zeros and talking about what they mean. The second question is identifying the vertex and talking about what it means. Again, we've already done this above. We said the vertex is right here. So the vertex is at 9. A vertex is a point, so I need both of those numbers. Any idea how I find the second number? You could estimate it from this graph, but we do actually know how to calculate it. If I wanted to calculate the revenue at $9, it goes back to how we were calculating in this table. If my price of the movie is $9, the number of downloads would be 18 minus 9, or 9,000 downloads. And then the revenue would just be 9 times 9, and the revenue would be 81,000, which is why it's a better price than 10, because you're making $1,000 more. So here I could say my vertex is at the point 981. And what does it represent? I'm going to have to write this up here. It represents that $9 is the best price of the movie to make the most revenue. And I can even say the revenue $81,000. There are different ways to word that, of course, but you want to include that $9 is going to result in the most revenue. Finally, this one we have not done yet. This one asks, what is the domain for the price of a new movie? And we had said domain is all possible inputs. And so when you think about this situation, we've got the entire graph here, but we want to think real critically, what type of numbers could our price of the new movie be? When we had talked about domain, we had said you want to think about, is there a minimum number, a maximum number? Do you want only whole numbers, or are you okay with decimals? These are all questions you need to think through to completely describe a domain. And so one of the first things I'm going to mention is, we had mentioned it earlier, if you're talking about price, it doesn't have to be a whole number. You can have decimals. We did all of our work with whole numbers, but we said your movie could cost $6.50. So when I'm describing the domain, I'm going to say all values. But can the movie be any value? Could the price be any number? Well, looking at our graph here, we're seeing it goes from -6 to 24, but in reality, that's not all of the possible movie prices. You cannot have your movie cost -$6 or -$3. $0 is the lowest it can go. So I'm going to say all values between 0, and my face is going to be in the way again, 0 to, well, we're seeing 18 is the most, or the highest price that we're looking at in this situation, because at $18, that's when it goes back down to 0. So that's our maximum. All values between $0 to 18. That would be our domain for this situation. So we've got a couple more like this below that are going to be for you all to try, you to pause the video and practice doing this. Because this is a skill that is going to be super helpful when we start looking at more graphs of quadratic situations and try to understand what they're communicating. So jumping in, this is what we had said we were going to be doing. I'm going to be giving you different descriptions and equations that represent some familiar quadratic functions from earlier in this unit. Each equation is going to have a graph, and for each of these, I want you to describe the domain, the vertex, the zeros, and then for the vertex and the zeros, make sure you're talking about what it represents in the situation. So here is the first one. This comes from yesterday's lesson where we were talking about objects falling after being dropped. We had written this equation here, and this is the graph that goes with it. So looking at this graph, go ahead and identify the domain, the vertex, and the zeros. Pause this video now to try it, and then come back to check your answers. Starting with the domain, we said domain describes all the possible inputs. So if we're talking about inputs, I'm looking at my x-axis. Again, I'm given this entire graph, but I need to think critically. My input here is time in seconds. And so the time in seconds can't actually be all of these numbers I'm seeing. You cannot have a time of -8 seconds or -4 seconds. So that it was a little deceiving getting this entire graph, because this part here over on this side, it's not possible. What is possible, though, is that time is anything between 0 or up. So looking at our graph stops at 2, 4, 6, 8, 10 seconds, but objects can fall for more than 10 seconds. That was just as much of the graph that we could fit on screen as possible. So for my domain, for time, I'm going to say all values, because time can be a decimal, all values greater than or equal to 0. That just means that 0 is our minimum, but there is no maximum. Objects can fall for however long they need to fall before they get to the ground. The second question asked about the vertex. We said a vertex is the highest or lowest point on our graph, on our parabola. Here it's going to be the lowest point. It's this point here in the middle of the parabola, and our vertex just so happens to be at 0, 0. The other thing we said we wanted to talk about is what the vertex represents in this situation. What does that point 0, 0 tell you? Well, it tells us that at 0 seconds, the object has fallen 0 feet. Basically, at the beginning of time, the object hadn't fallen yet. That's another way you could word it. And then finally, our zeros. Here, this graph only has 1. There's only one point where the output is 0, and it is that same point. So our zeros for this graph happen to be the same as the vertex. And again, the output is 0, meaning the object has fallen 0 feet. So this is one example of identifying domain, vertex, and the zeros. Here is the next one. This also comes from yesterday's lesson where we are looking at the height and feet of an object t seconds after being dropped. And so above, we were talking about how far the object had fallen. This time, we're focused in on the height of the falling object. Do the same thing, pause the video and identify the domain, vertex, and zeros, and also think through what the vertex and zeros represent in the situation. All right. Again, time is our input, so our domain is actually going to be identical to what we said above. Even though we have this entire graph, you cannot go backwards in time, and so we are starting at a time of 0 and moving forward. So I'm going to say all values, just because, again, time can be decimals and fractions, so all values. But this time, when we're thinking about the time, it's a minimum of 0 seconds, but there is a maximum here. Our object cannot fall below 0. You can't go into the negative feet. And so our object is hitting the ground here at this point. And so that's going to be where our maximum time is. So we're going to say all values between 0 and it's at this line here. We're counting up. Every line is 2. So 2, 4, that would be 6 seconds. All values between 0 to 6. Our vertex, because our parabola is facing downwards, our vertex is that highest point right here. And so our vertex is at 0 on our x-axis. Again, I could look at this and try to estimate what number that is, but we actually have the number somewhere. We see it right here in this equation. And so our vertex is at 0, 576. And that right there also gives us an idea of what the vertex represents. Here, our vertex is the highest point, and so we can say the highest height is 576 feet. When we did this yesterday, we had said that 576 is that starting point or the starting height. And so if you're dropping an object, it makes sense that its starting point is the highest height it's ever at, because after that, it's just falling down. And then finally, our zeros here. There is a 0 over here, but again, we have eliminated that as an option because it's over there in the negative time. And so there's only one true 0 that makes sense in this situation, and it's right there. That we started describing a little bit in our domain. It is at 6, 0. It's a 0 because notice the output, that y coordinate is 0. And 6, 0, if the output is 0, that is telling me the height is 0. So this is telling me at 6 seconds, the height is 0 feet, meaning the object hits the ground at 6 seconds. We've got one final one like this for you to practice right here. This goes back to our first lessons where we were looking at quadratic patterns. We had never looked at a graph of those quadratic patterns, I believe, but here's a graph to go with it. In the situation, the number of squares in a pattern where n is the step number is represented by the function n squared plus 4. One final time, identify the domain, the vertex, and the zeros. Our domain is going to be describing the input, which here is the step number. Thinking back to those lessons where we were looking at patterns, think about what those step numbers looked like. We had step 0, step 1, step 2, step 3, step 4. Those step numbers had to be whole numbers. All whole numbers. Notice our graph stops at step 3, 6, 9, 12, 15. I can't even see where the line is at that step number, but we know from those patterns you can go beyond step 15, right? I think some of our conversations we had talked about step 100 and what it would look like. Those step numbers can go on forever and ever. When you talk about whole numbers are the numbers 0, 1, 2, 3, 4, and so on. And so when you say the domain is all whole numbers, it means it can't be negative. Remember, all of our patterns started either with like step 0 or step 1. And so once again, we are eliminating this side of the graph. That is not true 100% of the time, but it is true in a lot of situations just based on what the input is. Our vertex here, because our parabola is going up, it's going to be the lowest point, which is right there. Our vertex is 0. And once again, we could estimate what that number is, but we do have it. It is right here. It is at 4. And what does that vertex mean? It means the pattern starts. I know it starts because we're talking about step 0. The pattern starts with 4. What's that 4 represent? 4 squares. And so it's starting with 4 squares, and it's just getting bigger and bigger and bigger. Finally, our zeros. Remember, your zeros are where the output is 0. If you're looking at a point, it means there is a 0 here. And if you're thinking about the situation, that 0 is the number of squares. What step number has 0 squares? Looking at this graph, none of them do. We just said above, your pattern starts with 4 squares and you're just adding more and more squares to it. Looking at our graph, there is no step number where the number of squares, the output, is 0. That would be a point that goes through your x-axis. So for this graph here, in this situation, there are no zeros. And we could even say no zeros because there is no step number with 0 squares. Please know that that is an option of something that could happen. You can have a graph that has no zeros, like this one. You can have a graph that has 1 0, like this one here, or above this one. Or you can have a graph that has 2 zeros, like the one we had done with revenue. I'm using the word zeros, but it's interchangeable with x-intercepts, right? This graph has 2 x-intercepts. This graph has 1 x-intercept. And this graph has no x-intercepts. That is the end of this lesson. Remember, in this lesson, we had talked about using quadratic functions to represent revenue. And then we also worked a little bit more on our understanding of these quadratic graphs by identifying vertex, zeros, and then going back and reminding ourselves about what domain is and identifying the domain of these quadratic situations. Thanks so much for watching. I hope this video was helpful, and I'll see you in the next one.